talking, but so in this session we are going to have 16 different papers. Each of them is going to be 4 minutes presentation, and the first one that we have is a best paper nominee, which is a little bit longer. It's going to be 10 minutes presentation, and it's called Reformulating Soft Dynamic Time Warping into Target Artifacts and Prediction Quality, presented by Johannes Tyler.
Hey ISMIR, good afternoon, and I'm very excited to present you today a way for reformulating the soft dynamic time warping loss, where we provide insights into target artifacts and prediction quality. My name is Johannes Zeitler. I'm a PhD student working at the International Audio Labs in Erlangen under the supervision of Meinert Müller. Let's start with a relatively common MIR task where we have an input recording and want to train a transcription model. And the transcription model should, for every time frame in the audio, predict a representation that contains the probability for node activity. In the example throughout this presentation, the input sounds like this. Now, in order to train such a transcriber, we typically need a large amount of labeled training data. And typically, we use strong targets that have a frame-wise correspondence to the audio and to the prediction. So our strong targets for the example sound like this. Now, as these targets correspond to the audio on the frame level, we can use a classical element-wise loss to train the network, such as MSE or binary cross-entropy. So training with these targets is very precise, and we get relatively good prediction results. But the question is, where do we get those targets from for real recordings? Of course, in the case of piano music, we can perform on a disc clavier and save the corresponding MIDI, which is a representation of such strong targets. But what happens if we want to train on historic recordings or on full orchestral symphonies? In this case, we would have to manually annotate every note event, which is, of course, infeasible in practice, at least for a university. So let's choose a different approach. Let's only annotate global segment boundaries in the input audio and in the musical score. And at least in Western classical music, we can be sure that the recording is performed exactly as it is written by the score. So from the score, we obtain information about which notes are played and in which order they are played. What we don't obtain is the precise duration of each note. For example, there might be a ritardando or a fermata. And that's why we call those targets that we derive from the score weak targets, because they only globally correspond to the input audio, but they may have local timing differences. So now, to train a transcriber on this kind of weakly labeled data, we still need some alignment. And one loss function that has such an integrated alignment step is the so-called soft dynamic time warping loss, or short SDTW. So now that we have established a pipeline for training with weak targets and soft DTW, let's take a look at the day in the life of a typical PhD student who uses these targets for his training. So the PhD student wakes up and the training is finished. Nice, it was training for hours. So the student is happy and checks the predictions, but they sound horrible. So there's so much blurring in the predictions. Some notes have a very reduced amplitude. So the student starts to think about the problem. It doesn't seem to be the network. It's the same one he's always using. Also, it's not the data. The segments are aligned precisely. So again, it must be something inside the soft dynamic time warping loss. And this loss is really complicated. Our student doesn't know what's going inside, so he doesn't know what to do. All he can do is basically adjust some hyperparameters and retrain the model. Training is taking 4 hours, so what does a typical student do during this time? right? He sits there and stares at the screen, right? What else should he do? And while he's doing that, he starts to think, what if there was a way that we could inspect the training with soft DTW before actually training? What if we could tell something about the training success before starting the training? So let's see what we can do to help the student. If the problem is not the transcriber and not the data, then it's the loss. And if the inside of the loss is complicated, then at least we can take a look at the gradients that flow from the loss to the network, because this gives us information about how the network parameters are updated in the end. Of course, we can write this down for soft DTW, but there's an alignment step involved and 2 recursions, and the formulation is complex, and it doesn't help us. So how do we help the student? In our work, we propose to reformulate the soft DTW loss. In particular, we take the internal states of the soft dynamic time warping loss and the weak targets, and we compute a virtual target representation, which we call modified targets. And now, interestingly, these modified targets have a temporal frame-wise correspondence to the predictions and to the input audio. So we can interpret the training now differently. We can interpret training with soft DTW and weak targets as training with frame-wise modified targets and an element-wise MSE loss. Note that we're not actually changing the training. It's only a way to interpret the complicated soft DTW training as easy as the training with element-wise features and an MSE loss, such as you see on the left-hand side. So if you read our paper, you will find a deep mathematical analysis of the soft DTW properties. We have some bad news for the student. So we prove that soft DTW causes blurring. Always. It's in the math. There's no way to avoid it. But now we have found a way that we can rate the amount of blurring, and we know how to control it. So let's take a look at a practical example where we want to fine-tune a pre-trained transcriber on weakly aligned data. So to do so, we train models with 2 different sets of hyperparameters, and we want to see whether we can predict the training outcome already in the initial phase. As a reminder, this is what it should sound like. So let's choose a first set of hyperparameters with a relatively high Softman temperature. And when looking at the modified targets on the left-hand side, we see that they already are quite blurred, and many nodes have a reduced amplitude. Again, these are the modified targets that we computed before even starting the training. So now let's train the network, and let's take a look at the final predictions on the right-hand side. Also, they have a reduced amplitude, and they also sound like the modified targets. So now we were able to predict this bad training outcome before even starting the training. So now we have a tool at hand that we can use to analyze the loss. And now let's choose a second set of hyperparameters with a lower Softman temperature. Now the modified targets look nice and crisp, and they also sound good. Very cool. So let's take these good targets virtually and use them to train the network. Let's listen to the final result. So now this final result is satisfying. It's almost as good as training with strong targets. And we were able to predict this good result before we even started the training. So to summarize, we took the complicated formulation of the soft dynamic time warping loss, and we mathematically computed a reformulation into a set of targets with frame-wise correspondence to the predictions. We showed that the network is indeed learning these targets during training. this visualization and representation is very natural, so we can interpret these targets. We can look at them and we can sonify them to hear what the network is finally going to learn. On the mathematical side, we provide theoretical explanations for many artifacts that are commonly found in soft dynamic time warping, such as blurring or a decay of the amplitude. Altogether, we really provide a tool to help the training and to understand the loss. So already at the beginning of training, we know what the network is learning. So thanks a lot for listening, and please meet me at the poster. Thanks.
So next one is ITO Master, Inference-Time Optimization for Audio Effects Modeling of Music Mastering Processors. Presented in person by Jung-Hyun Kong.
All right, hello everyone. I am Jung-Hyun, but also known as Tony from Sony. I will be presenting ITO Master Inference-Time Optimization for Audio Effects Modeling. Long title, but it's Inference-Time Optimization for Music Mastering Processors. I'm on behalf of my Sony collaborators. Yes, I'm here. So imagine where we have a system that helps users with post-production tasks, such as music mastering. This agent may perform very good, but still the user might want to adjust just a bit more from this result for a finer control, such as the user might want to have a result that has more of the reference style, or might want to combine with other references, or might want to see how the parameters are being changed from the initial result to another style's result, or might want to input a reference type that the mastering agent does not support. And we present ITO Master, which allows further optimization during inference time to allow all these scenarios for finer control on music mastering processors. First, we prepared the mastering agent that was trained with a self-supervised manner. So here, the mastering style converter's objective is then to match the style of a reference music. We designed the converter to either be able to produce audio signal directly or output audio effects parameters to for better interpretability of the mastering process. On top of the trained mastering system, we now can apply inference time optimization technique for further finer control. This method makes it very flexible to use when user is not satisfied with the initial result, or perform different applications of music mastering by changing either the reference signal or optimization objectives. For instance, users can optimize their result with text prompts to observe mastering change in terms of like semantics. So you can check out our interactive demo pages where you can try out your own sample. Yeah, just try it out. It's quite interesting. Thanks.
The next one is multidimensional approach to opera analysis, harmony, tempo, and dramatic interaction in Wagner Siegfried. It's presented in video by Pascal Smolensky, and Christoph is going to be in the poster session. You can go and talk with him after.
What is musical form, and how can we describe it regarding various parameters, like harmony and tempo? For example, in an opera by Richard Wagner. From its premiere on, the music of Richard Wagner's Ring des Nibelungen has been described as formless. That is because it lacks of typical features associated with the perception of musical form. For example, clear caesuras, typical harmonic and melodic closing formulas, a structuring in separated parts, e.g. aria and recitative, and so on. However, it is possible to observe coherent formal ideas on a large scale when form is understood as a dynamic musical process. In this view, the dramatic content of a scene is projected onto the music and actively shapes its structure. Such processes become visible through the progression of various parameters. In our study, we focus on tempo, tonal centers, and harmonic stability. For the harmonic analysis, we measure probabilities for tonal structures that rely on deep pitch class representations, here for Siegfried Act 3, Scene 1. Each band on the vertical axis represents one of the 12 diatonic scales. The gray scale represents the grade of probability. Dark black areas stand for a high probability and indicate a stable harmonic area. Light gray areas, mostly distributed across several bands, indicate an unstable harmonic structure. Furthermore, we use information from the Wagner ring dataset that contains many annotations for 16 recordings, like measure annotations, singer rolls, and many more. From the measure annotations, we compute the average tempo for each measure, as shown here for the 1980 recording conducted by Pierre Boulez. We then extend this procedure to all 16 recordings and derive a smoothed median curve, the thick red line, across the 16 versions to reduce the influence of individual performances. We overlay the scale probability graph with the median tempo curve and the singer roll annotations from the Wagner ring dataset to link the musical events with the present characters and dramatic content. The first scene of Act 3 is a conflict dialogue between Erda and Wotan, here referred to as Der Wanderer. It is clearly observable that the two characters are associated with contrasting musical profiles, particularly in their tempo, tonal centers, and harmonic stability. For instance, notice the contrasting tempo patterns and the harmonic shift between both characters in the middle part of the scene. At the dramatic climax, Erda adopts Wotan's faster tempo, and both characters move into harmonic instability, reflecting the peak of the dramatic tension. We observed a recurring pattern across all three scenes of Act 3, contrasting characters with distinct tempos and tonal centers and/or stability, converging at the climax into both shared tempo and instability. This suggests that Wagner's large-scale form emerges from dynamic processes that reflect dramatic conflict and resolution. In the future, this method could be extended to other parameters like dynamics, pitch, or instrumentation, and open new perspectives on performance analysis. Thank you very much for your attention. For further information, please see the paper or contact one of the authors directly.
So next is exploring the feasibility of LLMs for automated music emotion annotation, and it's presented in person by Meng Yang.
Hello, everyone. My name is Meng Yang from Sensi Lab, Monash University in Australia. Today, I'm going to present our work, which is exploring the feasibility of LLMs for automatic music emotion annotations. Emotion-related research is a focus point in the ISMIR community. Many of them require the music dataset with emotion labels. Existing dataset rely on human labeling, which is time-consuming, costly, and the scale of this dataset was limited to a few thousand pieces. But modern deep learning approach require much more annotated data. Therefore, we propose an automatic annotation method to let LLM infer the music perceived emotion from the metadata, as metadata is the key source for instrumental music. Our automatic pipeline uses music title and composer as a keyword for the web search and extract the relative information of the music from the target website. And then this context will be processed by GPT-4o to infer the perceived emotion based on the genre, the styles, the composition, and historic background, and etc. And using this method, we label the giant MIDI piano dataset, which is a classical piano MIDI dataset containing more than 10,000 MIDI files. We designed an evaluation framework to investigate whether LLMs can effectively annotate music emotion as human does. In this work, emotions labeled as 4-quadrant valence and arousal labels. We randomly select 400 samples, and 3 human experts will manually label the dataset and build a gold standard based on majority voting from the human labeling. We evaluate the annotation quality from 3 aspects: the accuracy, the inter-annotator consistency, and the distribution similarity. First, we use gold standard as a ground truth to calculate the accuracy of LLM's annotation. The accuracy of GPT-4o generated annotation is around 0.71, compared with other humans, which are all about 0.8. The performance of GPT is not as good as humans, but the result is still comparable. For inter-annotator reliability, Cohen's kappa is used to measure the pairwise agreement between 2 styles of annotations. And Flynn's kappa is the same indicator, but between the multiple readers. Our results show that GPT-4o's label differ more often from the gold standard than any single human expert, but its variability at the group level still remain within the range of natural human disagreement. And GS divergence is used to measure the similarity between 2 probability distributions. The result of GS divergence show a moderate level of similarity between the GPT-4o and the expert consensus. This suggests that GPT-4o could capture much of the collective expert. So above evaluation shows that GPT-4o does not yet match the human expert performance overall, but its variability is still within the range of natural human disagreement, and is still an efficient approach for the large-scale annotation. However, this method does have some limitations. The performance would depend on the quality of the metadata, and it may mislabel the work that differ from a stylistic norm. To summarize our work, we propose an LLM-based music emotion annotation method and develop an evaluation framework to investigate the performance gap compared with human annotation. Our findings show that GPT-4o does not yet match human expert performance, but the result is still comparable and within the natural human disagreement. So consider its efficiency, it still holds potential as a promising approach for the large-scale music emotion annotations. That's the end of my presentation. Thank you.
So next one is an evaluation strategy for local key estimation, exploiting cross-version consistency. And it's presented in person by Yiwei Yang.
Thanks, Gabriel, and hello, ISMIR, hello, everyone. Today I'm presenting our paper, An Evaluation Strategy for Local Key Estimation, Exploiting Cross-Version Consistency. I'm Yiwei from University of Würzburg, and this paper is co-authored with Yannick Venot and Christoph Weiss. So let's begin. So in 1827, this guy, Franz Schubert, he composed such a piece, and 200 years later today, we want to analyze the local key of this piece. So we find an audio recording of this piece, and we run our fancy deep learning model on it. And here we get a result. It starts on E minor, and then goes to B minor, and then to B major. Okay, looks all good. However, my colleague finds another version, another audio recording of the same piece, and they run the same model. and they get this result. It stays on E minor without modulating to B minor. So something must have gone wrong here. It is the same piece, just two different versions, and the same model, the model should always give the same output, but it doesn't. Then we think maybe we can evaluate this, we can measure this consistency as an extra evaluation strategy for local key models. So to make it systematic, we start with two versions of the same piece, which might be different in length, because different performers will interpret them differently, and we align them with DTW, giving us a warping path with many pairs, and each pair indicate 2 frames in 2 versions that represent the same musical content, from which the model should always give the same output. And for each pair in this warping path, we compute a similarity value, and then we average along the warping path, giving us a consistency value of this version pair. And we do this for all versions, and then average it again to get a cross-version consistency for this model on this data set. So comparing the cross-version consistency with standard evaluation metrics for local key estimation like recall and MIREX, we see that recall and MIREX, they are labor intensive because they require expert annotations. And cross-version consistency, it requires only cross-version data sets, even without annotations. And since in annotations for recall and MIREX, you have this nightmare of annotation subjectivity, and you never get enough data to model such subjectivity. And in comparison, cross-version consistency is annotation-free method, so no annotation, no subjectivity. And furthermore, we find that even if there are 2 measures, recall and MIREX, they are always highly correlated. And in comparison, we find cross-version consistency, it's still correlated to recall, but the correlation is weaker than between MIREX and the recall. So we think that we don't undermine the importance of the traditional evaluation metrics, recall and MIREX, and you should still compute them when there is label. But we claim that cross-version consistency is also useful as an additional figure of merit, and it can be used as an extra evaluation strategy. And we experiment with various models with multiple training runs with different checkpoints within each run, and we show that there is a rough correlation between in-domain CVC with in-domain recall, out-of-domain CVC with out-of-domain recall, and in-domain CVC with out-of-domain recall. This example here shows we train the model on one data set, and we compute the CVC and recall on another data set, and we see that there is a rough correlation. Therefore, we conclude that cross-version consistency can be a good proxy for models both in domain effectiveness and out-of-domain generalizability. So that's all. Thanks for listening, and if you're interested, please drop by our poster where we would love to have a discussion. Thanks.
So next, tuning matters, analyzing musical tuning bias in neural vocoders, and it's presented by Ulrich Fernandez in person.
Hi everybody, my name is Hans Ulrich, or short Uli Berdenes. I'm a PhD student at the International Audio Labs in Erlangen, and I'm happy to show our work on tuning bias in neural vocoders. And this work was done jointly together with Ben Maman and Manan Müller. So let's start by dissecting the title one by one. So what is musical tuning in the first place? Musical tuning defines, at least in a Western 12-tone equal temperament system, tuning defines the frequency of all pitches by means of a single reference frequency, or a single frequency for a reference pitch. And there's this modern standard that the note A4 has a tuning of 440 Hertz, but this is by no means universally applied, as we can see in the following plot. So this is a histogram distribution on a data set of Western classical music and the tuning estimates, and we can see that there's quite a lot of variety, and that 440 Hertz is not even the most used values because a lot of orchestras tune higher. So tuning is important in music. So what is a neural vocoder? So this is a common type of model in modern music generation pipelines, where you have first an acoustic model, which represents some latent representation, often a spectrogram or a MELD spectrogram, and then the vocoder's job is to estimate the time domain signal from that MELD spectrogram. And in training, we can simply encode like real recordings into this latent representation, like a MELD spectrogram, and then the vocoder has to learn to estimate back the time domain signal. So how do we analyze musical tuning bias in this system? So we take the same setup as during training. So we take a real vocoding, we calculate the MEL spectrogram, and then the vocoder's job is to reconstruct the signal. And now we can measure both tunings. So we can measure the tuning of the input, tau, and we can measure the tuning of the output, tau hat. And the central question we ask in this work is tau roughly equal to tau hat? Because for an ideal vocoder, this should be the case, because y hat should be equal to y. So what we can do is we can measure this tau and tau hat on a large data set, and we can have a scatter plot of tau over tau hat. And as I already mentioned, for an ideal vocoder, this would be a diagonal. But we found a lot of cases where this is really not true. So in this particular instance, the vocoder, like no matter what the tuning of the input is, the vocoder always changes the tuning back to roughly 440 hertz. And this is, in a musical sense, actually a big problem. And we tested a whole, different models, and we proposed some metrics how to measure these tuning deviations. But this is quite a severe case. We also found model configurations that are a bit better, at least, and also some that are actually pretty good. But if you now think, okay, I don't really care about the output of my tuning anyway, if it's 440, I don't care about it, then I have bad news for you, because we also ran an additional listening test, and we found out that in cases where the vocoder changes the tuning, like in this case here, the output quality suffers quite a lot if your input has a non-standard tuning. So you try to vocode a piece, which is like at 442 or something, and then the output quality is greatly reduced compared to if you vocode a piece with 440 hertz. We have a supplementary website as well. You can find the link with the QR code on the poster later, where we have some audio examples where you can really nicely hear this. Yeah, that's it. Thanks. Visit our poster, happy to discuss, and please be aware of tuning bias in vocoders.
So next, aligning text to music evaluation with human performances, presented in person by Jichen Huang.
Do you know how to?
No, I have it on Google Slides. There should be like a link for that.
You have this text. Okay. 여기 산사바고 독바하고 고정이 혹시 어떻게 되는지 알 수 있을까요? 여기.
Thanks. All right, so my name is William Huang, and I am happy to present our work aligning text-to-music evaluation with human preferences, done with collaborators from CMU, UCSD, Sony, and Cornell. So text-to-music systems have continued to improve, but evaluation lags behind, with the commonly used freshet audio distance being shown to correlate poorly with human preferences in certain cases. In this work, we conduct a systematic study of the design space of automatic music generation metrics. We search over this space via meta-evaluation on controlled syntactic degradations. And based on this search, we recommend MAD, or the mouth audio divergence, which we show is more sensitive to diverse degradations. And also to validate our results, we collect music prefs and open source human preference datasets And also we show that math correlates better with human preferences. So in this work, we focus on system-level reference-based metrics, where we have a set of generated music and want to compare it against a set of reference music. So this is typically done by embedding both sides of music and computing a divergence measure between the two sets of embeddings. So we have 3 dimensions in our design space. We have the reference distribution, we have the embeddings, and we have the divergence measure. So for reference distribution, we compared FMA pop against a set of internal commercial music. For the embedding things, we experimented with a set of more recent models, including self-supervised and generative ones. And for the divergence measure, we compared the projected audio distance against a set of more recently proposed measures. So we search over this space via meta-evaluation by controlled degradation. Like for a given quality aspect, we can generate sets of music of different qualities, and we can test whether these distinctions in the qualities can be reflected by the measures. So to begin with, similar to previous works, we can control fidelity by adding white noise to an audio piece. Let me play a quick example here. So here's an audio from the FMA pop set. And here's a noised version. Right, so different from previous works, we also consider aspects that are more relevant in music generation. For instance, we control musicality by perturbing music in the symbolic domain and synthesize everything under the same pipeline. So again, as an example, here's an original phrase from the LUC dataset. And here's a perturbed version. Right, so we also consider context and diversity in our experiments. We have more details on our demo page. So we started by looking at the different divergence measures, and we found that if we look at all 4 aspects, the recall and mouth measures perform better, with mouth being more consistent across different setups. And then we look at how the different embeddings perform when coupled with mouth and recall, and we find that self-supervised embeddings do perform better, and they outperform the more dated VGG-ish embeddings. So based on this search, we propose MAD, where we couple the MERT embeddings with the mouth divergence measure, and we show that this combination is high-performing and avoids the issue of generative models, evaluating generative models. So finally, to validate all this, we collect music prefs, a set of 2,500 pairs, human pairwise comparisons, and by comparing the human rankings versus the metric rankings, we show that the FAD variants do not correlate very well with the human preferences, whereas MAD performs a bit better. So yeah, our code and data are available online, and I'm happy to share more about this in the poster session. Thank you.
So next one is investigating music track liking in the Hall of Album Covers, and it's presented in person by Anna Hausberger, I think.
Hi, ISMIR. Really happy to be here to present you our work. When we think about listening to music on music streaming platforms, we most often focus on the music itself. But in reality, listeners are exposed to much more additional information, like the album cover. And all these elements together create like a complex user experience. So now when we take a look at available data sets for researchers, we see a very different picture. These data sets are often highly simplified with user and tracks being just these and most of the context information missing. But it might even be that these additional context information, like the album cover, might influence how listeners perceive or evaluate tracks. So in our work, we want to explore 2 research questions. First, to what extent can an album cover shown during audio playback influence the listener's liking of the music track played? And if such an influence exists, does it follow the halo or horn effect, meaning does a positive or negative impression on the album cover influence the liking of the music track? We explored these 2 research questions through a 2-stage survey study. In the first stage, the users were asked to rate 40 album covers and 40 song snippets separately and rate them how much they like them and if they know the artists or not, or if they are unfamiliar to them. In the second stage, which took place at least 36 hours after the first stage, they rated the song snippets again while an album cover is shown. And to probe for the halo or horn effect, we paired the album covers most liked by the individuals with the least liked songs. So we have had individual lists of pairs for each individual participant. So what did we find? First, we detected a notable change in the individual music track rankings, meaning that when we look at the ranked lists of items, we found that on average, only 1 item overlapped between stage 1 and stage 2 in the bottom and top 3 of each user. And for top and bottom 10, even less than 5 items overlapped in these ranked lists. We also found a significant correlation between how much they liked an album cover and how much the scores changed between stage 2 and stage 1, and also found that how they perceived the matching or mismatching between the album cover and the song snippet mattered, meaning that if they perceived the song to match better to the song cover, or if they liked the album cover better, they were more likely to rate the song snippet higher in the second stage of the survey study. So what could this mean? It could mean that we should take more contextual factors into account, as we show in our results that it actually changes the perception or the liking scores of the music tracks if we show them an image or an album cover that they like or dislike, and influence the user liking, yes. So let's have a discussion about this in the poster, and if you have any questions, I will be there. Thank you.
So, next one is Phylo-Analysis of folk traditions, a methodology for the hierarchical musical similarities analysis. And it's presented in person by Hilda Romero Velo.
안녕하십니까? 저는 스페인에서 온 일입니다. I'm Hilda from Spain. Welcome and thank you for joining this presentation. Let's talk about our traditions and dive into folk music. So my question is, if we listen to the world, is this what it sounds like? I mean, looking for similar musical patterns in our traditions is key to understanding our shared roots. This work proposes a methodology to explore musical similarity on a large scale. To evaluate it, we present an annotated dataset of 600 scores, half from Ireland and half from Galicia, a region in the northwest of Spain. Each score is labeled with its musical genre and segmented into musical phrases. To compare the scores, we look at 3 main features: diatonic intervals, chromatic intervals, and rhythmic ratios, combined to produce 5 different representations. So now, we can evaluate the score similarity at the feature level. To evaluate the score similarity, we look at different musical layers. First, we compare entire scores using the global alignment algorithm, which is commonly used by informatics to align biological sequences. Then we zoom out to the phrase level and introduced a novel approach to capture musical form. Long story short, we cluster similar phrases and check whether each pair of scores has some in common. So here we have two options. Ignore phrase order and check just the shared content, or focus on the structure of the music and keep the order of the phrases. And we have a third option, which is combine both approaches. So each feature encoding paired with a similarity method yields a distant matrix within scores, which is used to build the corresponding phylogenetic tree. One way to assess each encoding similarity pair is by studying how clearly genres emerge. That's why we infer a genre tree using the average distance between scores from different genres, and introduce a new metric, the genre separation ratio. Values above 1 indicate stronger genre cohesion and clearer boundaries. The results showed that the combined similarity with 75% form and 25% shared phrases is the best at inferring the genres. So some genres, such as alalas, slides, and strathspey, are easier to identify. Meanwhile, the Irish waltz from the session is the lowest genre separation ratio. After talking to Teresa Harkin of the Irish Traditional Music Archive, we found that the Irish waltz label in the session includes a mix of genres from includes a mix of tunes from different genres. So we have a problem there because different genres with the same pad. Yeah, that was the problem. So what about the findings? One of them showed that the Irish bar dance and the Galician rumba display rhythmic similarities worth exploring. After looking closer, we saw they share meter and subdivision with some accentuation differences, both being music for partner dancing. Another finding revealed this set of different phrases from different genres in the Galician tradition that are quite similar. I played them during the poster session, so you can hear how they resemble each other, so please reach out during the poster session. We would like to thank Folcoteca Galega and Xulus Jesus for providing access to the full archive of Galician traditional music and to our funding institutions. You have the code, the annotated dataset, and more details in this GitHub repository, and you can find more information through my link tree. 감사합니다. Thank you.
Next paper is dPLP, a differentiable version of predominant local pulse estimation, and it's presented in person by Sebastian Strahl. I don't know. Sorry, I'm really sorry.
Hey everybody, it's my pleasure to present our work here today. My name is Sebastian Strahl. I'm a PhD student at the International Audio Labs in Erlangen, and this is joint work with Jingyu Chu and Meinert Müller. To introduce predominant local pulse, or PLP for short, let us consider a beat tracking system. It takes as input an audio signal and outputs a novelty function that indicates for each frame the likelihood of a beat. To derive beat estimates from the novelty function, we could simply apply peak picking. But as indicated by the red dashed lines, some of the peaks were actually not detected. A reason for this could be that there are no clear onsets in the audio at these positions. To improve the beat estimates in such cases, we can compute the PLP function as a post-processing step. It enhances the local periodicity and thereby fills the gaps caused by the missing onsets. As you can see, applying peak picking to the PLP function gives much more regular beat estimates. However, one limitation of the PLP computation is that it's a non-differentiable operation, so it cannot be used within end-to-end trainable systems. It can only be used as a post-processing step that is disconnected from the training. In this work, we present a differentiable version of that PLP computation that can already be used during the training. To explain our modifications, let us have a closer look at how the PLP is actually computed. So starting from the novelty function, we first compute a tempogram that describes the similarities between short segments of the novelty function and sinusoidal kernels of different tempi. You can think of this as a spectrogram of the novelty function, where the frequency axis is given in beats per minute. For each frame, we then select the tempo that shows the highest similarity, and we use a sinusoid of that tempo to locally represent the novelty function. We do this for every frame, overlap and add all the optimal will-node sinusoids, and finally apply half-wave rectification to obtain the PLP function. As you can see, it nicely fills the gaps of the novelty function. One step that makes the PLP computation non-differentiable is the maximum operation used to select the optimal will-node sinusoid. So for dPLP, we replace this step by a weighted summation of all will-node sinusoids. Specifically, we apply column-wise softmax normalization to the tempogram, and we use the resulting weights to combine the sinusoids of all tempi. For the frame highlighted in blue, you can see that one tempo still dominates, but the others contribute as well, which makes this step differentiable. Again, we do this for all frames, overlap and add all the local representations, and finally apply half-wave rectification, basically the ReLU activation function. As you can see, the dPLP function lies somewhere in between the novelty function and the original PLP function, so it still enhances the local periodicity, but it doesn't modify the novelty function as much as the original PLP. But now we can integrate it into our end-to-end differentiable pipelines. And that's what we did in our experiment. So we did a beat tracking experiment using a spectral flux, a trainable spectral flux module as novelty detector. And the resulting novelty function was processed using dPLP using 3 kernel sizes. The novelty function and the dPLP functions were combined by a lightweight fusion mechanism. And if you're interested in the results of this experiment, whether the differentiability of the PLP module actually helped training a better spectral flux module, please visit our poster. Thank you.
So paper number 11 is PICNet-FP, peak-based neural audio fingerprinting robust to string time stretching, and is presented by Guillaume Cortés-Sebastien.
Hello, everyone. I'm Guillaume Cortés-Sebastian. I'm going to present our latest work on audio fingerprinting, PICNet-FP, peak-based neural audio fingerprinting robust to extreme time stretching. This work is a collaboration between BMAT, DISR, and the Music Technology Group. First of all, what is audio fingerprinting? Well, it's the technology behind music identification, the technology underneath famous music apps like Shazam or SoundHound, for instance. Then, what is time stretching? It is the transformation of the tempo of an audio without affecting its pitch. It is commonly used by DJs while mixing and in user-generated content platforms. Let's hear an example of a slowed-down version of Daddy Cool, for instance.
She's crazy like a fool. Why I'm Daddy Cool?
And now a sped-up version.
She's crazy like a fool.
And what do we mean by extreme time stretching? Well, we refer to the level of stretching that goes further than what has been previously studied in previous works, like factors of 0.5 or 2, which halve and double the tempo respectively. Peak-based audio fingerprinting approaches work on spectral peaks, which are a selection of the local maxima of the spectrogram, to later link them according to some heuristics and generate a hash from them. These systems are widely used in the industry. They're lightweight, efficient, highly scalable, and work well for the majority of cases. The main drawback is that they have an extraction limitations and are tailored to be robust to a specific distortion, so they lack of flexibility. On the other hand, neural audio fingerprinting systems work directly on the spectrograms in a contrastive manner to generate embeddings. Neural approaches have better identification results, are more flexible to different scenarios, and can capture more complex distortions. The main problem of these systems is that they do not scale well as peak-based ones, and require much more computational power. So we ask ourselves, why cannot we have the best of both worlds in a hybrid system? A system that would learn from the spectral peaks and perform a more complex linking using neural networks. So the main motivation of this work is to leverage in large industrial catalogs of already pre-computed spectral peaks by developing a model able to capture a more complex representation of these peaks while keeping the model lightweight and scalable. So here we present PigNetFP, which is a hybrid system that uses the hierarchical point set feature extraction from PointNet++ for the first time in MIR and combines it with the contrastive learning framework already used in the work of Chang et al. Neural audio fingerprint. We benchmark our model PigNetFP with the public available state-of-the-art in audio fingerprinting NeuralFP and with the traditional peak-based solution QuadFP, which is the state-of-the-art in time stretching. We perform the same query by example test as in neural audio fingerprinting work, but with a stretched data set. So the results show that both PigNetFP and NeuralFP perform significantly better than QuadFP, achieving the same performance in the commonly studied 0.7, 1.3 range. For a greater amounts of stretching distortions, PigNetFP performance gets close to NeuralFP. It is important to take into account that PigNetFP has 100 times less parameters than NeuralFP, while the input data, the spectral peaks, are 11 times smaller than the spectrograms used in neural audio fingerprinting. In conclusion, PigNetFP is the first hybrid peak-based neural audio fingerprinting system. It has a state-of-the-art performance on time-stretched data, and the model is 100 times lighter than NeuralFP, with an input data of 11 times lighter too. It is a promising approach and the first step to lighter neural network-based audio fingerprinting systems. Thank you for your attention and see you at the poster session.
Paper number 12 is generating symbolic music from natural language prompts using LLM enhanced dataset, and it's presented in person by Wen Dong.
Cool. Thank you for the introduction. So this is Herman from University of Michigan. You might recognize my name from the very long email I sent as the publication chair for the presentation materials. But I'm here to present on behalf of Weihan Xu. She's now at MIT Media Lab as a research assistant, and she's on the PhD market. So check out her profile if you're looking for talented students. So in this project, we are trying to do text to symbolic music generation. So recent years, you've seen a lot of audio domain text to music generation, but symbolic domain text to music generation has largely lagged behind. And so we think one of the biggest challenge here is the data set. So in this work, we are presenting the Metascore data set with 963K thousands of MuseScore files and MuseXML files where we have a bunch of rich metadata. So our goal in this project is to explore whether we can use this data set and to explore text to symbolic music generation where we want to have controllability on instrument, composer, difficulty, and genre, all enabled by this data set with rich metadata. So in this data set, we have all kind of metadata, and we also try to train a genre taker so that we can complete the missing genre information. So come to our poster to learn more about this data set. So to enable text to symbolic music generation, where we need some caption to train these models, so we use the LLM as a way to generate these captions. So the idea is to use a technique called in-context learning, where we basically provide a bunch of examples in our prompt, where we have the input, a list of text, and the output will be some example caption. And at the end, you will see that that's our input query, the text, and we want to generate a caption. So with that, then we can generate some caption to train our model. So the representation we're using is just based on the Remy Plus representation, where we basically sequentialize the whole symbolic music, the musical score, into a list of tokens. So we explore two different kinds of models. So first, we look at a more traditional way, tech-conditioned music generation system. So usually I look at it like, recipe, then cook, pipeline, where you basically list all the tags like genre, composer, difficulty as the prompt, and then you want to generate the rest of the musical tokens. And we also explore, because we are doing this free-form text conditioned music generation. And in this case, we basically grab sentence transformer that we can extract and embed in for the text input. And we use that and add it to the positional encoding and all the music encoding that we grab from the input, start of song tokens so that we can generate the rest. And so we do a bunch of evaluation, objective evaluation, but on top of that, we did subjective evaluation, where we see that we evaluate coherence, arrangement, adherence, and overall quality, where we see the tech-based model is actually doing better than the text prompt-based model. Why is that? Because if you want to do the text prompt music generation system, you actually need the text encoder to do extra work to look at the prompt. And we also do a comparison to a concurrent work text to media, where we show a comparative performance. So we present a new data set with a bunch of rich metadata with LLM-generated natural language captions, and we train two models with tech and text-based controllable music generation. So see you at the poster.
Paper number 13, a survey of vision to music generation, method, datasets, evaluation, and challenges. And it's presented in person by Zhao Kai Wang.
Hello everyone, and I'm Zhao Kai Wang. I'm from Shanghai University, Shanghai Jiao Tong University, and today I'm going to present our work. It's called A Survey on Vision to Music Generation, Methods, Datasets, Evaluation, and Challenges. And so here's a brief introduction. Our work is the first survey on the vision to music generation task, which includes video to music generation and image to music generation. And the applications can be like film scoring, games, short video creation, dance music synthesis, VR, and so on. And for the current status of this task, it is relatively underdeveloped because the relationships between vision and music is more complex than some general tasks like text-to-music generation. And also, there are few industrial deployment of this task. And in this figure, we present some representative works of this task. And in this figure, the paper CMT, which is the top left one, and vMuseProd is also from our team. And I want to mention that the CMT has received the Best Paper Award at ISMIR Multimedia 2021. Yeah, so, and this is an overview of the vision to music generation. First is the data sets. We can categorize these works by the input types and the output types. And for the input types, the input can be general videos, which includes films or short videos, and also the motion videos, which includes like dancing or sports or music instrument performance. And the input can also be some static images. And the output can be both symbolic music or audio music. And for the architecture of vision to music generation, it can be separated into different modules like vision encoding, vision music projection, and music generation. And all these three modules can model the vision music relationships of semantic and rhythm relationships. And evaluation, this matrix can be categorized into objective and subjective ones. And categorized by its purpose, it can be for the music-only metrics and metrics for vision music correspondence. And since we're running out of time, I will just go through these tables very briefly. And so you can refer to our paper or come to our poster session for more details. This is a table for the methods of vision to music generation with their image type or modality and this published date or music learns and so on. And these are the data sets which include the general videos, the human movement videos, and images. And we also summarize their like data source, modality, learns, and so on. And these are the evaluation metrics, which are the objective metrics like FAD or CLEP score. These are the more common metrics. And also there are some subjective metrics which we use the human study or by sending out questionnaires to collect these metrics. For the challenges of this task is like the lack of standardized objective datasets and benchmarks or limited customization and controllability in the current methods and so on. So you can refer to our paper for more details or come to our poster session. Thank you for listening.
So, number 14 is emerging musical properties of a transformer under constructing self-supervised learning, and it's presented by Yue Xuan Kong.
Hi everyone, my name is Yue Xuan, and I'm here to present our work with my 4 supervisors, Emergent Musical Properties of a Transformer under Contrastive Self-Supervised Learning. I want to start first talking about this general purpose contrastive learning from music signals. So a very basic framework is like this, where we take segments from different audios and we project segments from the same piece of audio closely to each other in the embedding space and segments from other audio far away from each other. And therefore, we have this embedding, this is what I just said. We project them like this in the embedding space, and we take this embedding space for downstream tasks. So we can categorize downstream tasks into 2 big categories. One is global tasks, where we classify one piece of music into one or multiple categories, such as music tagging or key estimation. The other one is local tasks, where we want to make prediction at a frame level, such as beat tracking or chord recognition, where we want to have a prediction at each frame. And I want to mention that it's quite counterintuitive to use this contrastively trained embedding space for local tasks, because we're projecting segments from different places closely to each other in the embedding space, which means that they're not aligned in beats or chords. So they might not be able to capture these local properties. Therefore, in this paper, we explore if actually by these general purpose contrastively trained models, we can also use them for local tasks. We take inspiration from this paper called Dino, where they basically showed that there are local emergent properties that can be used for local tasks in image, such as music segmentation. So we take this idea for music, try to see if actually by training a model like this, can we also enable general purpose contrastively learning models for local tasks. The way that we do this is that we take, again, 2 segments from the same piece of audio, and we patch them up, we add positional embedding, we also prepend a class token at the beginning of the whole sequence. So this is the classical way of training a vision transformer. And we pass it into a vision transformer. Then at the output, we apply a classic contrastive loss only on the class token. Then for downstream tasks, we take the sequence tokens and use them for local tasks. Then we take the class token and use them for global tasks, such as tagging and key estimation. Our hypothesis is that for this class token here to be able to differentiate segments from different audio, the sequence tokens needs to embed local properties such as beat and chord. Then we carried out a whole analysis, quantitatively, also qualitatively, to see if there are actually emergent properties emerging in the sequence tokens and if they're actually useful for local tasks such as speed tracking and chord estimation. I won't go through details here. If you want more details, please come at my poster. Thank you.
So, number 15 is INGP-HOT, a database of musicology annotations for popular music, and it's presented by Sergio Ramas in person.
Hello, I'm Sergio Ramas from SiriusXM and presenting this work on a dataset we have released called MGP-HOT, an analysis of music, together with my colleagues from SiriusXM. Okay, so this dataset came from the Music Genome Project. That is a very big annotation effort that lasts for more than 25 years, where a team of music experts have been annotating every year millions of songs with hundreds of very detailed music attributes. No? So this is a very structured and quality control annotation process. So I think this is arguably the most comprehensive musicological analysis of popular music to date, but it is private. No? So this is something we wanted to change. So after many years, we managed to release a subset of the Music Genome Project. In this case, it's more than 21,000 songs that correspond to songs that appear on the Billboard Hot 100 charts. And we released 58 musical attributes classified in 7 categories. So instrumentation, sonority, vocals, harmony, compositional focus, rhythm, and lyric topics. And what makes this dataset unique and different from other datasets already there? So first thing is annotated by music experts, and by music experts, so I mean they are musically trained musicians with a major in music theory, so they are very well prepared. Another thing is that the scores are in a continuous scale, so between 0 and 1 in a step of 0.1, so it's not a binary dataset like tag dataset, so there is scores that indicate the relevance of the attribute in the song. And also, there is a complete coverage of the analysis. So all attributes are scored across all songs. So a 0 means that there is no that attribute in that song. So this all reflects that the presence, the absence, and the intensity of attributes in music that is not found in any other data set. Also, the attributes are very detailed, like, for example, vocal breathiness. They are organized in 7 categories, as I said before, and we also provide text descriptions of each of the attributes. And this comes also with the chart data from Billboard, because it's associated with the Billboard dataset. So there are some limitations, of course. There is no audio, although there is a recent paper from MTG that solved this issue. It is US-centric, because it's based on the Billboard Hot 100, and there is a mainstream focus, of course, on the music there. So there are many applications we envision for this dataset, and to showcase this, in this paper we focus on the case study, that is the analysis of the evolution of popular music. So what we did is to plot the trend curves of all these attributes across time. So we see 2 examples here. For example, on the left, you see the harmony, the black one, so how it went from the 60s in a predominance of major harmonies to a more even distribution between major and minor harmonies nowadays. Or in the right, you see how synthetic sonority went very high on the 80s and also in the 10s. Then we try to identify music revolutions, so like in the famous paper of Matthias Manch, what they did with audio, we did here with the musical attributes, and we found, using the food novelty and the similarity matrix, that identifies similar revolutions that were identified in that paper from audio, and we extend with new revolutions. And then we also did an analysis by category, so using a subset of the attributes corresponding to a category, we identify when the revolution occurs for the different attributes. So for example, we had rhythmic revolution on the 60s, the sonority revolution was an instrumentation on the 80s, and then the vocal revolution, the last one, on the 2016. So yeah, we released this data set that is a unique data set. I hope this helped the community and everyone use it. Also, we did this analysis of popular music, so just come and check the poster and ask your questions. So thank you very much.
The last paper of the session is Music QA, Music Questioning Answering through Audio-Video Fusion, and is presented by Ana Maria Christodoulou.
Yes. Hello. So this is a very simplified version of how music understanding works for us humans, and what I, as a researcher, use to test music understanding in computational systems. This figure illustrates a crucial fact. Without multimodal processing, embodiment, and cultural awareness, neither us nor computational machines can really understand music. So I am Ana Maria Christodoulou. I am a PhD student at the University of Oslo in Norway. And today I'm very happy to be here and present to you our dataset Musical, a dataset for music question answering through audio-video fusion. So for those who are unfamiliar with music question answering, it is a computational task that aims to analyze and answer questions about music. Previous work has heavily prioritized audio-only methods, often overlooking the visual aspects that are very important to how we perceive music, and especially when we're talking about music performances. And furthermore, previously, music question answering often focused on simple descriptive elements, such as the first instrument that makes a sound is on the right or on the left. This is a guitar, this is a piano, which is very useful in question answering in general, but lacks real musical knowledge, and also lacks any sort of causal reasoning and the why behind music performance choices, engagement, communicative gestures, and so on. And lastly, many existing datasets in this field suffer from biases, inconsistencies, or too generic answers due to LLM-generated question-answer pairs. To solve all of these issues, our dataset Musical consists of 310 music performance videos, and it comes with almost 12,000 human-annotated question-answer pairs. And it is built on the premise that computational music understanding, similar to human music understanding, needs multiple modalities. And in this case, we have audio, video, and text. Now imagine that you need to ask, do the performers' visual cues coordinate with the rhythm of the music in this video? So to answer this, a system needs to focus its auditory attention to the rhythm of the music and its visual attention to the location and the movements of the performers, and then engage complex reasoning to understand, to make a connection between the rhythm and the movement, understand the question, and give an appropriate answer. Musical consists of a wide array of musical traditions and styles from all over the world, from jazz, raga, djembe, and Polynesian rhythms. It features instrumental, vocal, and dance performances, and this is because we aim to support machine learning systems in developing a kind of cross-cultural music understanding and actively addressing the gap of lacking genre and lacking cultural diversity in other datasets. We also introduced two new categories of questions, causal and purpose, where we can ask why certain things happen in a performance, why are performers dressed in a certain way, why did the audience cheer in a certain moment, and so on. Our questions are deeply grounded in musicology and music psychology to reflect how we interpret and understand music, and they're annotated by expert musicologists with backgrounds in ethnomusicology, music psychology, and music technology. And lastly, Musical serves as a new benchmark for this task. Our experiments with state-of-the-art architectures like Lavish and AVST reveal some strengths in certain areas and highlight further development in complex scenarios like ensemble performances. If you find this interesting, I will be happy to talk to you more about this, so please come visit my poster.